school instructor Stephanie, and in this session, we're going to be talking about number sense, looking at some of those arithmetic properties that you can expect to see on test day. So here we go. These are our objectives for this lesson. So after the end of this, you will feel more confident ordering rational numbers on a number line and also looking at some of this terminology, absolute value, multiples, factors, and exponents, both recognizing what those words mean and also how to solve questions that require use of those concepts. We'll also talk about how to add, subtract, multiply, and divide, as well as use exponents and roots of functions and decimal numbers to calculate certain quantities. All right, let's get to it. One of the first things we're going to talk about are powers. Now, powers are a way to show repeated multiplication. This is really just a way to make things more efficient. So for instance, if I wanted to say 5 times 5, I could say that as 5 to the second power, or 5 squared. And that's because 5 is being multiplied by itself 2 times. Now you could write this as 5 to the exponent of 2, or 5 to the second power. And we can see then that 5 squared is equal to 25, which is the same thing as 5 times 5. Now you can go the other way by looking at roots. Roots are a way of thinking about, okay, what number multiplied by itself this many times is going to give me the number in question. So for instance, if I wanted to know what is the square root of 49, or what is the second root of 49, what I'm really being asked is what number times itself twice will give me 49? And we could write that as the square root of 49 equals 7. Now, of course, if you're just doing it squared, that doesn't really save you a whole lot of time. But when you're thinking about powers in larger quantities, you can really see how writing them as exponents becomes a lot more efficient. So for instance, if I wanted to write 5 times 5 times 5, I could say that's 5 to the third power, or 5 to the power of 3. And I'd write that as 5 with 3 as the exponent, and that would equal 125. And of course, you can go the other way again as well. You can take the cube root, or the third root. And so again, you're asking yourself, okay, what number times itself 3 times will give me 125? And you'd express that as the cube root, or the third root of 125. And then of course, that would equal then 5. Now, any number raised to the first power is going to equal itself. This is one of several exponent rules that we're going to talk about in this session. So 3 to the first power is 3, 14 to the first power is 14, 125 to the first power is 1,325. Now here's one that's a little bit less intuitive. Any number raised to the power of 0 equals 1. So again, we can see that any of these numbers when raised to the 0th power equals 1. Now this is provable using some of the exponent rules that we're going to talk about a little bit later on in this session, but you don't need to worry about why this is to succeed on the GED math test on test day. For our purposes here, just know that anytime you see something raised to the 0th power, that can be replaced with a 1, because anything raised to the 0th power does indeed equal 1. And of course, you can also have negative exponents, but this isn't standard notation on the GED test. On test day, you're going to see those answer choices appear as positive exponents most frequently. So you can turn a negative exponent positive by putting it on the other side of the fraction line. So for instance, if you have 3 to the negative 2 power, you can rewrite that as 1 over 3 to the positive 2 power. And this could go the other way as well. So for instance, if you had a negative exponent in the denominator, you could put that again back over the fraction line into the numerator, and that would make it positive. And again, this is something that is provable with some other exponent rules we're going to talk about, but you don't necessarily need to understand why this is. You do just need to know how to apply it to certain questions on test day. Speaking of, let's go ahead and apply some of these concepts to question number 1. Now, at any time throughout this lesson, if you need some more time to think about a question, just go ahead and pause the video and then unpause when you're ready to review. So we'll do that right now. Pause the video, and when you're ready to review number 1, unpause, and we'll continue. Question number 1 is asking you which expression has a value less than 0. So if you're looking for a quantity less than 0, this means the answer choice must be negative. One of the most straightforward ways to approach this question would just be to start evaluating each of those answer choices. So let's look at answer choice A. Well, 1/2 squared, this is going to be 1/2 times itself twice. And when you're multiplying fractions, remember you multiply straight across. So multiplying the numerator, 1 times 1 is 1, and the denominators, 2 times 2 is 4. for a total answer of 1/4. Well, this is not less than 0, so we can eliminate answer choice A. Now, answer choice B is asking for -2 quantities squared. And here it's really important to note that the negative sign itself is inside this parentheses. That means that that negative sign is also going to be part of the number that you multiply 3 times. So -2 cubed is -2 times -2 times -2. Well, anytime you have a negative times a negative, that becomes positive. So -2 times -2 is +4. But look what happens when you have 4 times -2. A positive and a negative, it's going to give you a negative. So -2 cubed is -8. You've in fact already answered this question, so there's no reason to do any more work than you need to. Go ahead and just bubble in or select answer choice B, and you are done with question number 1. Now, you can simplify expressions when you have the same bases. So these are some of these exponent rules I mentioned a little bit earlier. So when bases are multiplied, add the exponent. So here we have 3 to the 4th power times 3 to the 2nd power. Well, 3 to the 4th power can be written as 3 times 3 times 3 times 3. And 3 squared can be written as 3 times 3. Well, if you look at this, you can see that you have 3 multiplied by itself 6 times, or 4 plus 2 times, as it were. So when you have the same base and you are multiplying those together, add the exponents. So 3 to the 4th times 3 squared is equivalent to 3 to the 6th power. Now, going the same way with exponents here, if you have x times x to the 3rd, in essence, there's kind of an invisible 1 there with that x, right? Because remember, anything to the 1st power is itself. So you can think of this as x to the 1st power times x to the 3rd power. You can write this out and see that you have x to the 1 plus 3, or x to the 4th power. Now, going the other way, if you're dividing exponents that have the same base, then those exponents would be subtracted. And again, you can see this if we actually write this out longhand. Now, you don't need to write this out longhand on test day. That's in fact the whole purpose of exponents, is to avoid having to do all that work in order to take some really long expression and make it a bit more efficient. But here we can see that if you do in fact write out 3 times 3 times 3 times 3 and divide it by 3 squared, 2 of those 3's will cancel out and you are left with just 3 times 3, or in this case, 3 squared. Now, this will also work if you have an exponent that's larger in the numerator. Larger in the denominator than in the numerator. This is when we might have some of those negative exponents. If you apply this rule, we have the same base, these are both base 3, and you are subtracting, you will in fact get 3 to the 2 minus 4 power, or 3 to the -2. Well, again, if you put that negative in the denominator, that would become positive. So this is going to equal 1/3 squared. And again, like I said, you can rewrite this as 3 to the -2nd power as well. So both of those are equivalent terms. So depending on how it appears as an answer choice, you may in fact see this with a negative exponent, or you may see it with a positive exponent and that exponent there in the denominator. Now again, same thing is going to work even if you have variables rather than numbers. X squared divided by x to the 4th, x to the 2 minus 4 power, or x to the -2. You can, of course, rewrite this as 1/x squared, because anytime you want to take a negative exponent and make that exponent positive, just flip it over that fraction line. Now, you can simplify radicals as well, and you can do that using the product rule or the quotient rule. Where the product rule is stating that when you are multiplying 2 radicals together, assuming those roots are the same, in this case, both of these are the just square root, we've got that square root sign, you can expand that, so the square root of x times the square root of y is the square root of x times y. So let's see how this would work with some numbers. The square root of 7 times the square root of 2 is going to be the square root of 7 times 2. Or you can rewrite this as the square root of 14. Now, you can also go the other way. So if you want to simplify the square root of 54, you can ask yourself, well, what are some of the numbers that multiplied together give you 54? Those are called the factors of 54. And in fact, we're going to talk about factors a little bit later on in this lesson. So we can say, well, 9 times 6 will give me 54. And the nice thing about selecting 9 as opposed to, say, selecting 2 and 26 is that 9 is itself a square number. Now, you can rewrite this as the square root of 9 times the square root of 6. And what number multiplied by itself 2 times will give you 9? Well, that's going to simplify down into 3. And so this can be simplified down to 3 times the square root of 6. All right, let's try this with some variables now. So you want to break this up. Let's see, is there a square factor here with x squared and y? Well, if we rewrite this as the square root of x squared times the square root of y, indeed, you can find one variable multiplied by itself will give you x squared, and that's going to be x. So this can be simplified down into x times the square root of y. Now, the quotient rule is when you are dividing radicals. So you can break up a fraction under a radical into its numerator and its denominator. So the square root of quantity, x over y, is the same thing as the square root of x divided by the square root of y. So let's look at this one here. The square root of 9/4, we'll break it up. This is going to be equivalent to the square root of 9 divided by the square root of 4. What number multiplied by itself gives you 9? What number multiplied by itself gives you 4? There you go. That is 3/2. And so that's another way to simplify some of these radicals. Again, it's going to work the same way if you have variables rather than numbers. We'll break it up, and then the square root of x squared is x. And the square root of y to the 4th. All right, well, what multiplied by itself will give you y to the 4th? Think about those exponent rules we looked at earlier. Y squared times y squared will be the equivalent of y to the 2 plus 2 power, or y to the 4th. So the square root of y to the 4th is y squared, and this will simplify down into x divided by y squared. Now, scientific notation is another way of using exponents to write out very, very, very large or very, 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 very small numbers by using powers of 10. So for instance, 10 to the 0th power is, well, you know this one, right? Because anything to the 0th power is 1. 10 to the 1st power, again, still an exponent rule. Anything to the 1st power is just itself. 10 squared, this is going to be equivalent to 10 times itself twice, or 100. 10 cubed, 10 times 10 times 10, or 1,000. And of course, you can get larger and larger and larger and larger. Now, you can, of course, also go the other way. So 10 to the negative 1st power is equivalent to 1 over 10 to the 1st power, or 1 over 10. 1 to the negative 2nd power is 1 over 10 squared, or 1 over 100. Again, we can get smaller and smaller and smaller and smaller. Now, the utility of this is when you have very large or very small numbers. So we could write out 2 times 10 to the 0th power, or 2 times 1, which is 2. 2 times 10 to the 1st would be 2 times 10, or 20. And you can see how the larger or smaller the number gets, the more useful this becomes. So rather than having to write out, say, 2 million, you can write out 2 times 10 to the appropriate number of exponents. And how you figure this out, again, going the other way, we get smaller and smaller and smaller. So what we're looking at here is the power of 10 tells you how many places to move the decimal to the right or to the left. So for instance, if you have a positive exponent here, you would put that decimal right after, of course, whatever integer value you have here. 10 to the 3rd power means move that decimal place over 1, 2, 3 times to get 2,000. If you have a negative exponent, let's see, like 10 to the negative 2nd, then you'd sit here, you'd think about that decimal right there after the 2, and you'd move it to the left 1, 2 spaces. Or here we go, look at this 1, 2 spaces to the left. So scientific notation tells you how many places to move the decimal after that first integer value. Positive exponents mean move it to the right, and negative exponents mean move it to the left. This is going to allow you to simplify really, 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 really large and really, really, really small numbers. So let's see how that would work in a test-like question. Right. I'm going to give you some time again to think about this one on your own, and then we'll walk through it together. So pause the video, take as much time as you need, and unpause when you're ready to continue. Now, question number 2 explicitly asks you to write the answer here in scientific notation. And of course, you can see that all the answer choices there are written in such a way. You have some sort of number up here, and then over on this side, you have some power. 10 to the negative 6, 10 to the squared, etc. Now, you have these cilia. There are 2.0 times 10 to the negative 4 meters wide. We want to know how many of them are going to fit on a slide that is 25 millimeters wide. Well, let's divide the width of the slide by the width of a single cilium. That's going to be the kind of math involved here. And to do this, let's rewrite 25 in scientific notation. So if you think about putting a decimal place after the 2, 25 millimeters is going to be what in scientific notation? It's going to be 2.5, again, putting that decimal place right after that first integer value. And then you'd have to move this to the positive to the right in one direction in order to make 25. So 2.5 times 10 to the first. And again, you can see that because if you move this over 1 to the right, you get 25 millimeters. So now we can rewrite that in scientific notation. To do an expression with this, take a look at the integer values first. So 2.5 divided by 2.0, that's going to be 1.25. And now evaluate the powers of 10. So 10 to the first divided by 10 to the negative fourth. Use those exponent rules from earlier. 10 to the first power divided by 10 to the negative fourth. Since you're dividing, you will subtract those exponents. And 1 minus negative 4 is going to be the same thing as 1 plus 4, or 5. So the final answer is 1.5 times 10 to the fifth power, or answer choice D. Let's look at another question that's going to this time ask you about roots. Now in this expression, the square root of 15 times the square root of 12, it's asking you to simplify the expression completely, but leave it in radical form, as opposed to just putting it in, say, decimal form. All right, think about those root rules that we reviewed earlier. Pause the video and unpause when you're ready to see the answer explained. Rather than sitting there and thinking about what 15 times 12 is, let's go ahead and rewrite these with their factors. So 15 can be broken down into 5 times 3, and 12 can be broken down into 4 times 3. Now if you rewrite this as you combine it, you can see that the square root of 5 times 3 times the square root of 4 times 3 is equivalent to the square root of 5 times 3 times 4 times 3. What this allows you to do is rearrange these, because you can see here that 3 times 3, if you have the square root of something multiplied by itself, well, that's canceling itself out. So in some ways we can think of this as the square root of 3 squared times 4 times 5. Well, breaking up each of these into these individual components, the square root of 3 squared is 3, and the square root of 4 is 2. And that leaves you with 3 times 2 times the square root of 5. 3 times 2 is 6. So this can be simplified down into 6 radical 5. And that will be the final answer that you'll want to enter into the text box on test day. Now, GED math questions may also ask you to solve multiple arithmetic expressions using the order of operations. So you can remember the order of operations thinking about the acronym PEMDAS, P-E-M-D-A-S. You always want to first evaluate anything inside parentheses or brackets, and second, move on to anything that has an exponent or a root. After that, you're going to move from left to right. So multiplication and then division, moving from left to right, and finally addition and subtraction, moving from left to right. Let's see what this looks like with an actual expression. Okay, so to evaluate this mathematical expression right here, first start inside those parentheses. So we're going to have to look at the 5 minus 2. That's inside those parentheses. So 5 minus 2 then is going to be 3. All right, now that we have 3, evaluate those exponents. So here you have 3 squared, which is 9. Moving from left to right, what operation would go next? Well, we're going to start with that multiplication. So 3 times 9 is 27, and 27 times 6 is 162. Finally, go ahead and add 2 plus 162 is 164 for the final answer. All right, here's one for you to try on your own. You know what to do by now. Pause that video when you're ready for the explanation, unpause, and we'll continue. Did you remember to follow the order of operations as you tackled question number 4? So the first thing you want to do then is work inside those parentheses. Now, inside the parentheses, we're going to have to follow order of operations again. So within those parentheses, you're first going to have to do the exponent. And then to simplify inside the parentheses, now you're going to have to do that division. So 28 divided by 4 is 7. This finally allows you now to get to those parentheses. So 6 minus 7 is -1. Now you can multiply. 3 times -1 is -3, and -3 plus 5 is -2. So remember, when you have an expression like this, it's almost like you have to do the order of operations nested inside an order of operations question. Start with those parentheses, but then once inside them, continue to follow the order of operations again until you have everything simplified down into a final answer. In this case, answer choice D. Number lines are how you will express these quantities, whether radicals, exponents, fractions, integer values, decimals, from least to greatest. And number lines are always smallest all the way on the left, and they get larger as you move to the right. So you can see here we've got negative numbers on the left and positive numbers there on the right. So as you move right, just like you would read from left to right, as you move from left to right on a number line, the values are going to increase. And then, of course, going the other way, if you look at it from right to left, then those values are going to decrease. Now, like I said, number lines don't always have to have integer values. They can, in fact, express fractions or mixed numbers. And these are the ones you'll most frequently see on test day. So in this case, we have those fractions as well as some of those mixed numbers there. Now, absolute value is, by definition, the distance of something away from 0 on a number line. So if I'm looking for the absolute value of 2, well, 2 is 2 spaces away from 0 on my number line. Now, -2 is also 2 spaces away from 2 on the number line. Distance can only be positive, right? You can walk 3 miles to the right, you can walk 3 miles to the left, but you cannot unwalk 3 miles. Right? Cheeseburgers don't count in that particular situation. So absolute value is always going to be a positive quantity because distance is always positive. So absolute value is written with 2 straight lines around a number. So if I wanted to express the absolute value of -2, I'd write it like this, with those 2 lines around -2. And this is one way of thinking about this, is saying, all right, so -2 is how far away from 0? Well, it is 2. Anything inside those 2 lines must be positive. Now you can also see expressions written inside an absolute value sign. For instance, what is the absolute value of 2d plus 6? Now, if you knew what d was, let's say d is 1. Well, 2 times 1 plus 6, that's going to be the absolute value of 8, and 8 is 8 away from 0. If d was -4, let's plug in -4 for that d. So this is going to simplify down into the absolute value of -2. We know that -2 is, again, 2 away from 0. So anything that's inside that absolute value expression must be positive. So to find the distance between 2 points, find the positive difference between those 2 values. So for instance, if I wanted to find the distance between 3 and -2, I could say, well, 3 minus -2, that's going to be the absolute value of 5. You could also, of course, on a number line, kind of count up, and you can see there's 1, 2, 3, 4, 5 spaces between the 2. Now the absolute value of -2 minus 3, so we could go the other way around. So if we took 3 minus -2, you'd see we get the absolute value of 5. And we could also take the absolute value of -2 minus 3, and notice here that you would still get 5, because absolute value is always positive no matter which direction you look at it. Keep that in mind as you approach question number 5. Again, pause the video, take the time that you need, and unpause, and we'll review. So question number 5 is asking you to calculate the distance between 2 points A and B. Well, even though it's most frequent to see, in this case, A minus B, remember you can also go the other direction, because in this case, the absolute value of 7/8 minus 1/4 isn't an answer choice. However, you can also go the other way, the absolute value of 1/4 minus 7/8, and that is an answer choice. That's in fact answer choice C. All right, let's do another one here. We got some mixed practice covering some of the concepts that we've looked at in this first part of the lesson. Which of the following expressions has the least value? Pause the video and take a moment to calculate question number 6. Unpause and we'll review. For this question, you're going to want to evaluate each answer choice individually, and then of course select the one that answers the question. All right, so 3 to the negative third power, that's the same thing as 1 over 3 to the positive 3 power, or 1 over 3 times 3 times 3, or 1 over 27. Now, 4 to the 0th power, in the 0th power is 1. You can already go ahead and eliminate answer choice B because you know that 1 over 27 is less than 1. So we can go ahead and get rid of answer choice B. Now, answer choice C, 4 to the 1st power, that's 4. That's even larger than answer choice B, so we'll go ahead and get rid of answer choice C as well. And finally, 2 to the negative 4th power, rewrite this with a positive exponent. This is equivalent to 1 over 2 to the 4th. 2 to the 4th is 16. So which of these has the least value? Well, the larger the the larger the denominator, the smaller the number. So answer choice A is the smallest. And you can think of this as if you were cutting, say, a pie into 16 pieces, as opposed to cutting a pie into 27 pieces, which piece would be smaller? I know I personally want you to cut the pie into just 4 pieces, so like a nice big piece of pie. But in this case, we can clearly see that 1 over 27, 27 slices of the same pie is going to be much smaller than 16 slices of that same pie. All right, here's another practice question for you to work on. Go ahead, pause the video and unpause, and we'll review. Anytime you have a lengthy word problem, always make sure that you are addressing what the question is asking. In this case, you want to know how many blocks did Bob walk to complete his errands? All right, well, Bob walks 5 blocks east, and then 6 blocks west, and then another 2 blocks west, from his apartment to the barbershop to the grocery store and to the post office. And then he has to walk back. So Bob still needs to walk back home. We don't necessarily know the route Bob takes from the post office to go home, but we do know that he's already walked 13 blocks already. So it's safe to assume that the only answer choice feasible is answer choice D, or 16 blocks. Time to look at a couple more vocabulary terms from our lesson objectives. I'm talking about factors and multiples. Now, in fact, we've already been looking at some factors when we were simplifying those radicals. Remember, I was talking about those numbers that multiply to give you one of the numbers. That's a factor. A factor is any number that divides evenly into another number. So, for instance, factors of 10 include 2 and 5, because 2 times 5 is 10. All pairs of factors that can be multiplied together can be created by using something called a t-chart. So, for instance, I could find all the factors of 10 by starting with 1 and saying, okay, 1 times 10 gives me 10. And then saying 2. Does 2 go into 10? Well, it does, 5 times. Does 3 go into 10? No. 4? No. And I'm already looped back over here to 5. So I'm now positive that I have gotten every single one of the factors of 10 written out in my t-chart. You can also, of course, look at negative numbers. So, of course, -1 and -10, and -2 and -5. So once you have all those positive factors, you can go and look at the negatives as well. The greatest common factor is the largest factor that 2 numbers have in common. So to find the greatest common factor, use a t-chart to find factors of the first number, and then use a t-chart to find factors of the second. As soon as you have a number that matches in the right-hand column of that second t-chart, you're done. That is going to be the greatest number that divides evenly into both numbers. So let's look at an example. If you want to find the greatest common factor between 48 and 72, start by making a t-chart of 48. I'm going to start with 1. 1 goes into 48, 48 times. Move on to 2. 2 goes into 48, 24 times. Does 3 go into 48? Yes, 16 times. What about 4? 12. Okay, does 5? No. Does 6? Yes, 8 times. And 7 does not go into 48, and you can see now that you've kind of looped back around. You've looked at all the integers between 6 and 8, so you know that you are done. All right, now we're going to do the same thing with 72. So 1 goes in 72 times, 2 goes in 36 times, 3 goes in 24 times, and now you're going to stop because you have a number that matches in the right-hand column. So 24 is the greatest common factor. This is the largest number that will divide evenly into both 48 and 72. There's no reason to continue writing out factors because you can see that any factors that you would continue to write out for 72 are going to be smaller than 24. So that's why you can stop as soon as you find one in that right-hand column that matches. Now, multiples result from multiplying one number by itself. In fact, anytime you were finding an exponent, you were finding multiples of that original number, right? 3 times 3 is 9. 9 is a multiple of 3. 3 times 3 times 3 is 27. 27 is a multiple of 3. So the first two multiples of 2, you can also think of these as counting by. So you can count by 2's to get multiples of 2. And here we go, 2, 4, 6, 8, continue. Now every number has an infinite number of multiples, right? We can continue counting by 2's or 3's or 5's or 10's forever until someone tells you to stop. So think about factors and multiples can be really helpful when you're simplifying. And of course, you're also using these concepts when you're simplifying roots and when you are expounding on exponents. Just like you could find the greatest common factor, you can also find the least common multiple. Now, there's no reason to find the greatest common multiple because, again, multiples go on forever. So the greatest common multiple is going to be somewhere out there in infinity. But you can find the smallest number that two numbers will multiply into. So start by listing out multiples of the first number, and then start by listing out multiples of the smaller number. Stop when you find a match. So we'll do an example here. Find the least common multiple, or the LCM, of 20 and 30. So start by listing out a few multiples of that larger number, 30, 60, 90, 120, and then start by listing out some multiples of that smaller number. Again, counting by 20s, 20, 40, 60. And as soon as you find a match, you're done. That is the smallest number that both 20 and 30 will multiply into. So just a table to kind of summarize the difference. Factors are found by dividing. So if you want to find factors of 10, think, okay, you can divide something into 10. Multiples are found by multiplying. If you want to find multiples of 10, multiply 10 by something. Factors are always less than or equal to the original number. Multiples are always greater than or equal to that original number. And finally, factors are few. Every number only has a finite number of factors, but multiples are many. You can have an infinite number of multiples. Time for some mixed practice. I've got several questions here for you to do. For each of these questions, just go ahead, pause the video as you see the question, and then unpause when you are ready to review your work. Question number 8 is asking about a container that holds 16 servings. And if each serving is 6 ounces, how many ounces does the container hold in all? Well, if we have 6 ounce servings and you have 16 of them, you can multiply those together to find the total amount in the container. So for instance, 16 times 6 is 96 ounces. That is in fact exactly how many servings we're going to have. So that's going to equal answer choice D. Take a look at question number 9. You know what to do by now. Question number 9 is asking how long is the remaining piece in feet? Well, we have a wooden dowel that's 12.5 feet long, and Jamie cut 2 pieces that were each 3 3/4 foot long. So you have 12.5 feet. Now in this case, it might be easier to think of these as decimals, only because 1/2 and 3/4 are fairly quick to decimalize. You can think of these almost as, quarters, right? 1/2 of a dollar is 50 cents. 3/4, that's 3/4, or 75 cents. So we've got 12.5 feet and 3.75 feet. So if you have this 12.5 foot dowel and you cut 2 pieces that are each 3.75 feet long, you have 5 feet remaining. This question is asking, how long is that remaining piece? It is indeed 5 feet long. Okay, pause the video and tackle question number 10. At the end of this 2-hour period, what is the temperature in degrees? Well, it starts off at 92 degrees, and then it goes up 12, down 5, up 6, down 3, and up 13. Well, if you write this as an expression, we'll just use this order of operations. And remember, when you're adding and subtracting, you just move from left to right. So 92 plus 12 minus 5 plus 6 minus 3 plus 13, you can just calculate this straight across, and that equals 115 degrees, or answer choice C. Question number 11 contains a number line. Remember that number lines get larger as you read from left to right. Go ahead, pause, and tackle question number 11. One way to address question number 11 is to use a combination of strategic elimination and rewriting your initial value. So right away, you can know that negative 16 over 6 is negative. So it can't be answer choice D, because answer choice D is some positive number between 1 and 2. All right, now rewritten as a complex number, we can rewrite this as negative 2 over negative 2 and 4/6. And that's because 6 goes into 16 2 whole times, and you are left with 4/6 remaining. Now, negative 2 and 4/6 is going to be somewhere between negative 2 and negative 3. Only answer choice B, point B, is between negative 2 and negative 3, and you can see that right here on the number line. Answer choice C, or point C, is somewhere between negative 1 and negative 2. So answer C would be something like negative 1.5, whereas answer choice A is somewhere between negative 4 and negative 5, maybe something like negative 4 1/3. All right, here is one of our last questions, or our last question, in fact. So go ahead, pause the video, and finish strong with question number 12. Question number 12 is asking you how many sheets of paper will be left over. All right, well, paper only comes in packages of 400 sheets, and a student buys enough paper to fill 3 binders of 150 sheets each. So let's see how many pages the student needs to fill those 3 binders. If each binder contains 150 sheets of paper, then the student needs a total of 450 sheets. If the packages only come in 400 sheets, how many packages does the student need to buy? Well, 1 package is not going to be enough. So the student had to buy 2 packages, because there's no way to go to the store and just buy half a package. So the student had to buy 800 sheets of paper. The student only needed to use 450. So the remainder is going to be 800 minus 450, or 350 sheets left over. And that matches answer choice C. All right, now that you're at the end of this lesson, you should feel more comfortable and confident adding, subtracting, multiplying, dividing, as well as using exponents and roots to address arithmetic operations that involve fractions, decimals, as well as integer values. You'll also more comfortable, hopefully, having a better sense of some of these terms we've talked about, absolute value, multiples, factors, and exponents, that when you see those concepts on test day, you know how to simplify and solve. Remember, you can always reach us at gedhelp@kaplan.com anytime you have a question or need some guidance as you continue to study and prepare for test day. Thanks for watching this lesson on demand. Happy studying and good luck on the GED test.